Thank you very much. So I have 15 minutes, yeah?
Right. 4 to 5. 5 for questions.
5 for a question, okay. So, thank you for being here. So my talk will be on Lorentzian metrics, Lorentzian geometry. So if you don't understand anything, then please ask. Or maybe the other option is to sleep. Yeah, it is. Okay, and I would like to thank the scientific committee and the organizers, and especially Mohammed, who is not here. But maybe there are many Mohammed. Yeah, this is a problem when we say Mohammed, especially here in Morocco or in countries like also Algeria and countries like this, because there are many persons named Mohammed. And also because in general, the first name is not enough to determine the person. The map which associates to a person his first name is not injective. The inverse problem is not well posed in this situation. And my talk will be on a kind of inverse problem. So I am interested in Lorentz metrics, okay? And to them, we will associate something like first name, maybe second name, etc. And we want to know if, with all these invariants, we can recover the Lorentz metric. Okay. In fact, I will talk more about Lorentz metrics, but many, almost all, apply to Riemannian metrics, which are more familiar for a priori for many people. And even the situation is better in the Riemannian case, okay? Okay, so in general, MG will be a pseudo-Riemannian manifold, and you know, we can associate to such a pseudo-Riemannian metric something which we call scalar curvature. It is defined exactly in the same way as in the Riemannian case. For the general pseudo-Riemannian case, the definition is exactly the same in the pseudo-Riemannian case. Why? Because if you remember the definition of the connection, what you need to define a connection, the Levi-Civita connection associated to a Riemannian metric, you need just to take the inverse matrix of the metric Gij. This you have. You don't need the fact that the metric is positive definite. Only that it is non-degenerate, and so it has an inverse. So you have formally these Christoffel symbols, which are equivalent to having a natural associated connection. And so by this you can, in particular, you can write the geodesic equation, and you can also define the curvature because you have a connection, and with help of the metric you can contract and get the Ricci curvature and also the scalar curvature. So all this is defined in the same way for general pseudo-Riemannian metrics. Okay, and this correspondence pseudo-Riemannian metrics to functions, which associate to a metric its scalar its function, its scalar curvature function. This is a covariant mapping. It is a natural mapping. It is a natural operator, if you want. To mean that if we apply a diffeomorphism to the pseudo-Riemannian metric, which we consider its image by a diffeomorphism, it is the same thing as applying a diffeomorphism to the function. Applying the diffeomorphism to functions means composition with the inverse of the diffeomorphism. Okay, so this is of functor. This is a covariant functor. This, which associated to metric, is scalar curvature. Okay, so we have this scalar curvature, and this is not the unique scalar. This is not the unique functor like this. Functor, to me, it is something natural. Okay. So I will give a definition of functors like this, and my concern is to see if, when we know all these functions, do we know the metric itself? Okay. So how to define general invariants for Lorentzian metrics? Again, I am defining things for Lorentzian metric, but you can think about the Riemannian case. Okay, Lor here is the space of Lorentzian metrics, and C infinity the space of C infinity functions, and an invariant is a map from the first space to the second one. So a metric, I associate a function, which is natural, as I just said. If I apply phi here, this is the same thing as applying phi on the right side. And we also add some homogeneity requirement. If I multiply the metric by a constant, then I will get the same thing, but to some power on the functional side. For the scalar curvature, D is 2, yeah? If we multiply by the sphere, for instance, of radius R, its curvature is 1. No, D is minus 2, sorry. D is minus 2, yeah. Okay, and the other condition is that when the metric is flat in the Lorentzian is the same as in the Riemannian, then I get 0. There is no invariant. And the other more important requirement is that this invariant, I can get it, it is an algebraic differential operator. It depends as a polynomial on the metric and on its derivatives, and also on the inverse of the metric. Okay? Like, because this is what happens. Why the inverse? Because this is what happens for the scalar curvature. We cannot just take something which is polynomial on the metric itself. All these is written in a coordinate system. This is the matrix Gij, but the rationality requirement does not depend on the coordinate system. Okay? So the example, the first one is that the first by which I started, but we have other ones. The Ricci tensor curvature is a tensor of the same type as the metric. So it has eigenvalues when I write it with respect to the metric. The eigenvalues are scalars, scalar functions. Okay? And so the eigenvalues of Ricci are scalars, and the norm of the curvature tensor. You have the curvature tensor. You can write, you can take its norm with respect to the metric, and you get scalar function. Okay? Yeah, we had this morning an example by Stefano. He's not here, Stefano. Yeah, and this morning about the chain conjecture, where he said that this A, if I well remember, the shape operator, it can have norm which is 0 without being 0. Okay, and this is why, because we take the norm with respect to pseudo-Riemannian metric. The norm associated to pseudo-Riemannian metric on tensors like the curvature is pseudo-Riemannian norm, and not. If we start with the Lorentzian, we get something which has big signature, and not necessarily Lorentzian signature in general. So the question is the inverse problem. we know all these scalar invariants, and we want to determine the metric precisely. And the point is why we choose scalar invariants and not tensorial invariants. So this is the point. I will come back to this later on. Okay, and one situation, special case of this question is when the space is CSI, to mean constant scalar invariants. All scalar invariants that we can define are constant. So the example is homogeneous space. Homogeneous space is space for which the isometry group acts transitively. So if I take a function if I take an invariant, by the naturality of the definition of invariant, this function will be invariant by the action of the isometry group. And because the isometry group acts transitively, so this function has to be constant. Okay? If instead, this is one motivation to study, to consider scalar invariants and no tensorial invariants. If instead of scalar invariants I have tensorial invariant like the Riemann curvature, then first it has no sense to say that the Riemann tensor is constant. And in addition, even if the space is homogeneous, the Riemann tensor is not constant in any natural meaning, if you want. Okay, so this is the interest to consider only scalar invariants here. And the special, so if the space is homogeneous, then it is CSI. Any scalar invariant which is a priori function, is here a constant. A natural question here is, is it true that the converse is true? I mean, if we have a space with all constant invariant, then it is true that the space is homogeneous. A particular case of CSI is VSI, vanishing scalar invariants. Any scalar invariant is zero. So here, we hope that the space to be flat. Yeah? Okay, so what do you think about this? Do this imply the space is flat in the Lorentzian case? And what in the Riemannian case first? Yes, just take the norm of the Riemann tensor. The norm is, this is a scalar invariant, so it is zero, so the Riemann tensor is zero. In the Lorentzian case, okay, we have the Riemann tensor, we consider its norm, or square of the norm. It is zero, but this does not imply the Riemann tensor is zero. The Riemann tensor will be just light, will be null, isotropic in some pseudo-Euclidean space, and yeah, this is the difference between pseudo and Riemannian. Okay, so this is a priori not true, but in fact there are examples. There are very beautiful examples, and even homogeneous examples. Okay, there are Lorentzian spaces for which any scalar invariant is zero, but these spaces are not flat. Okay, by the way, I have not defined Lorentz metrics. So Lorentz metrics are pseudo-Riemannian metrics with only one minus, yeah? And to what they are useful to, in particular, general relativity. Yeah, the Lorentzian metrics, they were the third geometry in the first talk of this meeting by our chairman. Yeah, the third geometry, if you remember well, it was Lorentzian geometry. Yeah. Okay, and. So what is plane wave? Plane wave is a Lorentzian metric which has this form, okay? in some coordinate system. There are many other definitions, but the most important fact is that here the coordinate system is u, v, x1, xn are in all are n plus 1, and u is in some interval, yeah? And maybe you can see here that 0 plays a particular role, but what we can prove is that we can find, if we have a space with one coordinate system like this, we can find a coordinate system around any other points where this point plays the role of 0 in this coordinate system. Okay, this is one important fact. Okay, and here you see that this space admits similarities, admits mapping like this in the coordinate system, which the mapping like this multiplies the metric by a constant. Phi star of G is lambda square of G. So there is special conformal transformation with the constant distortion. Okay? Yeah, you see that they are not homothéties in the Euclidean case because we don't have the same coefficients everywhere. You have lambda square and lambda, and on U you have just one. There is no action. Okay, so this is reminiscent to the homothéties of the Heisenberg group, which acts by lambda square on the center, but just lambda on the something supplementary to the center of Heisenberg. Okay, and just applying the homogeneity requirement and the naturality, we see that any scalar invariant has to be 0 at 0. But because 0 is not special, then everywhere any invariant has to be 0. Why I am talking about the fact that 0 is not special? Because if you apply translation do not preserve the metric, yeah? Because there is a quadratic behind du square, there is something quadratic, yeah? So if we apply translation on xi, the metric change. But there are other isometries which give us homogeneity when u is fixed. Okay? So we have an example of Lorentz metric, which is VSI without being flat. Why it is not flat? This is also easy to prove, by computation or by conceptual argument, if you want. So natural question is to classify all the VSI Lorentzian metrics. Yeah. No, not necessarily. It depends on you. It depends on you. There are examples where, if U is constant, then this is locally homogeneous. This is symmetric space.
It depends on H.
Huh?
Depends on H.
On H, yeah, absolutely. But we can have HU, for instance, not constant but homogeneous, because the action is not linear. They have a quadratic action, like the Heisenberg action on R. Okay, so it is natural and interesting question to classify all the VSI Lorentz manifolds. For instance, we have this example and we can ask if this is a unique example. Yeah? Okay. So now we have definition of scalar invariance, and we have an example of VSI. What we can say more, and for this let me give you some definition that you know in the Riemannian case, and they are exactly the same. So Mg is always a pseudo-Riemannian manifold, and N is a submanifold, and here I am defining what is the fact that n being totally geodesic. So if n has dimension 1, this is usual notion of geodesics. Yeah. So there is no parameterization even if in dimension 1. But what if n has higher dimension? So the definition is that, so this is a submanifold in M. The definition of totally geodesic is that if I have a vector which is tangent to the submanifold, the geodesic determined by this vector is contained in the submanifold. Okay, so the sphere S2 in R3 is not geodesic. Okay, because the geodesic is straight line and is not contained in the sphere. But a plane, an affine plane or an open subset of an affine plane is totally geodesic in R3, and they are the unique totally geodesic surfaces of dimension 2 in R3. Okay, so the other equivalent definition is when we take two vector fields tangent to n, then their covariant derivative is also tangent to n. And this is the first definition. The second one is we say that n is light-like if when we restrict the metric to n, we get something which is not a metric. We restrict the Lorentz metric. When we restrict the Lorentz metric to submanifold, we have three possibilities. Either we get the Lorentz metric on the tangent space, or a Riemannian metric, it can be positive definite, or something degenerate. There is a kernel, there is a radical of the metric in the tangent space. And in this case, we say that n is light-like. And what happens in this case is that this kernel has dimension 1 and no more, because we are in the Lorentzian case. The difference between the Lorentz and the general pseudo-Riemannian higher index is that isotropic spaces have at most dimension 1. Okay? And the metric restricted to the light-like is positive, but not definite. Okay? Okay, with this definition, and now the most important definition here is we say that Lorentz space is of Kundert type if there is a foliation by light-like geodesic hypersurfaces. So foliation, you know, it is a partition locally which is locally modeled hyperplanes, parallel hyperplanes, diffeomorphic to that. But here what we require is that it is not only diffeomorphic in some sense, but even isometric in some sense, because we ask the leaves to be totally geodesic, exactly as in the case of affine hyperplanes in the Euclidean space. But they are totally geodesic for the metric G, and we assume them also to be light-like. If a Lorentz space admits such foliation, then we say that it is of Kundert type. And one example where we have this is the plane waves space. Here, U equals constant. When we put U equals constant, the metric is all this part. The metric is only the last part. If U is constant, then du is 0. The levels of U equals constant. The metric restricted to these levels of U is just the Euclidean metric, on one variables. So you see that the dimension of leaves here is n plus 1, the dimension of the space is n plus 2, but the metric on the leaves, U equals constant, is the Euclidean metric. And they are totally geodesic with respect to this metric. This can be proved easily in this case. So this is what we require in general for space to be counted. And what is the theorem? Is that VSI implies Kundert. Okay? VSI means all the curvature, scalar curvature invariants are 0, and this implies Kundert. So this looks like these examples of plane waves, but Kundert is weaker than plane waves, really very weak than plane wave situation, but still this is something, this is strong condition. So there are many contributions to proof for the proof of this fact, of partial proofs of parts of this result. But what I want to explain today, yeah.
15 minutes.
15. Yeah, okay. Okay. Okay, so what I want to explain, but very really partially, yeah, if we have Lorentz space which is VSI and analytic, just to simplify for today this, and if through any point, yeah, sorry. So what I want to partially explain in this 15 minutes is that if we have a Lorentz metric which is VSI and analytic, then through any point I have totally geodesic like hypersurface. Okay? So what remains to prove that this is Kundert? It remains to prove that what I get is not something at random, but I have foliation. If we are in R3 and at any point we take an affine plane, the whole picture is not a foliation. We cannot get with this foliation. We have to be sure that if at one point I have this plane, and if I consider another point in this plane, then the plane that I get at this point are the same. Okay? Foliation means that when we have the leaf through one point and the leaf through the other point, they are where they intersect, in fact they are tangent. And this is enough because we are in this geodesic situation. Just to be sure that the intersection of these hypersurfaces here are tangent and not transversal. If they are tangent, then they are locally the same. Yeah, because they are totally geodesic, exactly like geodesics in dimension 1. So the point is to see how, from where we get this geodesic hypersurface, but I don't think I have time for this. And the second point is why it is very restrictive to have totally geodesic hypersurfaces in any situation, Riemannian, Lorentzian, and any situation like this. And after that, with this random, maybe random hypersurface, how to get foliation. Okay, so this I have no time to talk about, but just in some words, yeah. You know, there are many analogies between Lorentzian and Riemannian metrics, but there are differences. The main difference is that we have a variational problem in the Lorentzian case, in the Riemannian case, but not in the Lorentzian case. We have causality theory in Lorentzian case, but not in the Riemannian case. And we have what is called in general, special and general relativity, we have relativistic effects. Relativistic effects are dilation of time and contraction of length, and the meaning of relativistic effects is exactly the non-Riemannian behavior of Lorentzian metrics. In general, Lorentzian metrics behave exactly like Riemannian ones, but sometimes this is not the case, and this is in particular what happens in the case of special relativity, because special relativity has a big symmetry group, the Lorentz group, and if we add a phi if we add translation, we get the Poincaré group. And it is for this that we have a non-Riemannian behavior. And the general philosophy here is that for Lorentzian metrics, anytime we have non-Riemannian behavior, then we have a conduct structure. Okay? For instance, VSI, being VSI, vanishing scalar invariance, is something non-Riemannian, is a non-Riemannian character. Then necessarily we have a conduct structure. Having a non-compact isometry group on a compact space M, this is a non-Riemannian behavior, then necessarily we are conduct. Okay, this is general philosophy, if you want. So my second, all this was the introduction, and it seems that I will stop with just the introduction. And okay, so one question is why the curvature? I called my invariance scalar curvature invariance, but a priori I define them as some quantities which are functional on the metric, on Gij and the inverse and the derivatives. But yeah, the first point is to prove that in fact they depend only on the curvature, and this is perhaps the most important message to young people here, is that all is encoded in the curvature, but not the scalar curvature and scalar invariance on the true curvature, which is the Riemann tensor. Okay, so how to express this? This is a long story. Maybe in the third edition of this conference, I will come back and explain this. Okay, so what I want to add here is just yeah. How much time I still have? If it is positive, yeah.
Only just.
I still have 7. Oh, yeah, great. Okay, so maybe I will explain something here. No, not this. Yeah, I will explain just this. Why it is very something very special to have totally geodesic hypersurfaces. This, I think, yeah, you can think about the Riemannian situation. So, again, remember the definition of geodesic submanifold. S is such a submanifold. So, being totally geodesic means that when I have direction tangent to the submanifold, then the ambient geodesic is contained in S. Equivalently, this means that the second fundamental form is 0, the shape operator is 0, or that the geodesic, the intrinsic and the extrinsic geodesics are the same, all of this. But we have one-dimensional geodesics, of course, but we rarely have totally geodesic surfaces, for instance, or hypersurfaces. Okay, and in fact, okay, so there is a theorem by Élie Cartan, this one. Assume that you have a Riemannian manifold, to simplify, and assume that everywhere, at any point of the Riemannian manifold, you take a tangent hyperplane. Assume that this tangent hyperplane is tangent to some totally geodesic hypersurface. Equivalently, consider the exponential image of this tangent hyperplane. Now you have the exponential map, and consider the image of the exponential map of an open subset around 0 of this tangent hyperplane. So you get something which is a union of geodesics through the point where you take the exponential. So geodesics through this point are contained in this S, this image, but the problem is if you consider another point and another direction, there is no reason that this to be contained in this S. Assume this happens, then the metric has constant curvature. Okay? And this is to compare with the Dini theorem, which says that if metric is projectively flat, then it has constant curvature. Okay, so this is the extremal situation where everywhere we have totally geodesic hypersurfaces. But what is important is here is to consider intermediate situation. We don't have geodesic hypersurfaces everywhere in all directions, but we have many, let's say, and we have at least one. So again, the idea here is to say that even in this situation, in this partial existence situation, we have rigidity. Yeah, of course, when we say that the curvature is constant, the sectional curvature is constant, this is optimal. This is a strong conclusion. So what happens when we have not in all direction, but many things like this? Then this is the one thing that we have to consider in order to prove that VSI implies conduit. Okay. So what? Yeah, let me give you some examples. Yeah, the idea of why geodesic hypersurfaces are rare, they are not easy to find, is the same thing as Killing fields. Okay, Killing fields. The equation of Killing fields is you have many equations and you have how we say overdetermined or overdetermined. Yeah, the same thing if we write equation for geodesic hypersurfaces, we have many equations we cannot solve. And I think this is why, in general, we consider instead minimal surfaces, hypersurfaces or anything, or CMC, etc. Why? Because we have one equation. Like one equation we can solve and many equations we cannot. Because we have many compatibility to satisfy. Now, this is, yeah, okay. Okay, I think, just maybe to finish, let me give you an example, a concrete example and also an exercise. This one, S2 times S1. This is a very simple symmetric space, Riemannian space. Test Cartan theorem in this situation. You will see that if you take two tangent plane, in general, you don't have geodesic surfaces. Okay, just to see, and in fact, we can, in this situation, we can classify all totally geodesic surfaces in this situation. And okay, this is perhaps all what I can say for today. Okay, thank you.